Hi everyone. In this mini lecture, I'll be talking about JavaScript's built-in array method filter, and I'll also be talking about how we can use this to implement a basic spell checker. So first, just to start, filter, you give it a function and an array that it's called on, and it's going to take the items from the array for which the function returns true, right? So this function should either return true or false, and it's going to repeatedly plug in each item as an input to the function that you give it, each item from the array, and the items for which the function returns true, it's going to keep them, and the items for which it returns false, it's going to exclude them, right? So it gives you this. One thing I should mention is it's not changing the existing array. It's producing a new array, like this, a new filtered array that only contains the elements for which the function returned true, right? And one thing I'll mention here is that we're going to be traversing the items of the array itself, not the positions or indices of the items. So we're not going to be using this square brace of index, as we'll see in this example that I give. So let's say you wanted to take an array and get a filtered array from this one that only contains the positives in this array. So we have this function get positives that I'm defining here, and you give it the input of ARR, which is going to be our array, and you're going to have, I'm going to call this variable positive array, that's going to be the filtered version of this array that only takes, you could see, the positive numbers. And again, you see a function here. You don't just see num greater than 0. You see num arrow num greater than 0. If you just put num greater than 0, you would get an error. It would say, I don't know what num is here. Or that would basically be the error. You would get a reference error. So you have this function, reference to a function here. And as you can see, whatever number you plug it in, it's just going to check if that number is greater than 0. So just to give the and then it's going to return that positive array, right? So just to give an example here, if I give an array 3, -2, 0, 5, 42, -10, -8, 7, it's first going to, this is going to be what our ARR is, right? So this is going to get substituted for ARR because we put this as the input for get positives. And then this is going to be the array for which filter is called upon. So it's going to start with the 0th element in the array. So it's just going to give the 3, and it's going to ask, is 3 greater than 0? And it's true, so it keeps this one. And then it's going to go to the next item in the array, the one at ARR of 1, right? So it plugs in this -2 to num, and -2 is not greater than 0. So that's going to be false, so it's going to exclude that. And then it's going to try 0, which is ARR of 2. It's going to plug that in for num, and it's going to say 0 is greater than 0, and that's false, right? So it's going to exclude it. And then it would try the next element in the array, 5, the one at index 3, so it's going to plug in 5 here. And then it's going to ask, is 5 greater than 0, and that returns true. So it's going to keep that. And it keeps going, right? So 42 would be true. If you plug that in, -10 is not greater than 0, so that's false. So it doesn't keep that. -8 is not greater than 0, so that's false. So it doesn't keep that. And finally, it does 7, and 7 is greater than 0, so it keeps that. So you get this new array here. Again, it doesn't change the existing array. You get a new array that only has the positives from this array that you gave it. So it has 3, 5, 42, and 7. So it also preserves the order, right? And again, it's just because you could imagine creating a new array, starting with the first element. If that's positive in this case, it keeps it, and it just keeps going through the list. And every time it gets to the next number where this winds up being true, when you plug in that number, it adds that to the end of the array, right? So it keeps the same order. Now let me mention that if you were to go through the indices, rather than getting 3, 5, 42, and 7, you would get the positions of those. So you get 0, 3, 4, and 7, right? Which happens to also be the number. It's not only the index, it's also the number at that index, right? So that would give you an array that we wouldn't really want. We want the actual positives, not where the positives are located. So instead, we just filter on the array itself rather than using range 0 to arr.length to get the indices of the array. Okay, so we're going to use this for this basic spell check. So you can imagine that a way that you could implement a spell checker is anytime someone types in a word, it compares that word to the words in a dictionary. And if the word is in the dictionary, then it's spelled correctly. But if it's not, you're going to need some suggestions as to what the word was probably going to be, right? So some possible suggestions of corrected words for this misspelling. So in order to figure out how we're going to implement this, first I want to introduce this concept of edit distance or Levenshtein distance. And what that really is you're talking about the distance between words here. And when you're talking about the distance between words, what does it mean for two words to have a given distance between each other? So by distance here, we're talking about the minimum number of single character edits. And these single character edits are going to be insertions, right? So we add a new character, deletions, so we remove a character, or substitutions, so we change one character for another, right? And it's the minimum number or the smallest number of these single character edits that we have to make to get from one word to the other. So you can imagine from getting to the word that the person typed in to a word in the dictionary. So just as an example, if we wanted to find the edit distance between kitten and sitting, this is an example from the Wikipedia page. You could take this K initially and substitute an S. So that's sitting with one character edit, one single character edit. And then you change the E, you replace that with an I. So now we're up to two character edits. And then finally, you go and you add a character at the end. So you insert a character, and it doesn't have to be at the end, but in this case, that's what makes it sitting, which is what we want to get to, right? So we insert the G at the end. So we didn't use any deletions. This is the smallest number of single character edits we can make to go from kitten to sitting. So we would say that the edit distance is 3 between kitten and sitting. And notice that it would be, if we said the edit distance between sitting and kitten, it would be exactly the same. It would still be 3. We just go in reverse, and like over here, instead of inserting G, we would remove it. Instead of replacing the E with an I, we replace the I with an E, and instead of replacing the K with an S, we replace the S with a K, right? So that's what we would expect when we're talking about distance, that if the distance from A to B is 3, then the distance from B to A is 3. I guess that wouldn't always work out sometimes if you're talking about traveling from one place to another, because you might not be able to use the same roads to go back as you would forward. But in general, if we talk about the straight distance or the line segment that connects 2 points, the distance between A and B should be the same as the distance between B and A. You have the same line segment. Okay, so how are we going to use this for spell checker? Well, first of all, let me just say that we have this natural module, and a module is just a collection of related functions. So JavaScript doesn't have these functions like Levenshtein distance, but you can use a module, use code that someone else has written, functions that someone else has created to compute the Levenshtein distance, right? Because writing a function to compute the Levenshtein distance would be beyond the scope of this class. So over here, this is just a variable to hold all the functions that are in this natural module that are accessible here. And we just use the Levenshtein distance of this natural module, natural.Levenshtein distance, and we give it the inputs of kitten and sitting, and we could see that the distance between those two words is 3, right? So again, the natural module, it has more than this, than the Levenshtein distance. It has other things as well. It has other functions as well, and that's for really natural language processing. Okay, so getting back to how we're going to use this for spell check. So as I mentioned, a good first step on this would be to say, okay, here's the word, and if it's misspelled, let me look at all the words in the dictionary and see the ones that have the closest Levine-Stein distance. So maybe we want to look at all the words that are one away in the dictionary, or all the ones that are two away, right? And these could be our potential suggestions. But one thing I want to also mention is that something like yes with a capital Y and a capital S, or yes with a capital E and a capital S, is spelled correctly. But in the dictionary, it's not going to appear like this. It's probably going to be all lowercase letters. So what we want to do to make sure when we're comparing these words to say that yes, this is spelled correctly, um, would be to convert this to lowercase and then compare it to the lowercase version of the dictionary. The lowercase version of the words in the dictionary. So like capital Y and capital S, it would just go lowercase y, lowercase e, lowercase s. And lowercase y, capital E, capital S, again, would just go lowercase y, lowercase e, lowercase s. So they would both be going to the lowercase version, and they would be considered the same if they have the same case. So we do this, the word that person types in, and also all the words in the dictionary when we're looking to see if it's spelled correctly. So, and we'd also use this for the Levine-Stein distance. So this would be the general idea. You could also, by the way, make it so that you were comparing uppercase versions. It really doesn't matter. But this would be the general idea: is convert the word to lowercase, and then get all of the words in the dictionary. If it's not spelled correctly, get all of the words in the dictionary that are a Levine-Stein distance of, let's say, one away, or all the ones that are like less than, three away, so one or two. So these would get similar words that would only differ by the given word by one or two characters, and these would be our suggestions. Now, let me mention that in practice, this is not how spell checkers actually work. First of all, calculating the edit distance can be time consuming. It's not something like quick like addition. So if you were just comparing two words to see what the edit distance is, that would be pretty fast. But you could imagine that if you take one word and are computing the Levine-Stein distance between, let's say, 10,000 words in a dictionary, so you're doing this Levine-Stein distance calculation 10,000 times, then it winds up being, it's pretty slow. So this is not how, like, when you type it into Google, how it's actually being done. Because the other thing is, in addition to being slow, it's not even going to be the best suggestions all the time. So, for example, if you were doing acceptable, you might spell it with an I instead of an A, or you might spell it with an S instead of an A, since S is located right next to the A on the keyboard. But it's unlikely that you would spell acceptable with a V, right? So, I mean, these are all a distance of one away from the word acceptable, because you just make the replacement of A with I, or A with S, or A with V. But this isn't likely to be a misspelling, whereas these two would be likely to be much more likely to be a misspelling. So what something like Google can do, where they get lots of searches, is they could use data on to get like common misspellings of words, right? So they have tons of data that they can go through to sort of guide the decisions, and then they could make this. They could store these misspellings of common words so that you wouldn't have to wait for these calculations all the time. So they can do things a lot quicker. So, like, again, you could, right now, for instance, you could make a spell checker that just takes this as the data, commonly misspelled English words, something like that, to make your spell checker more accurate. Okay, but doing this where we're taking ones that are, let's say, one or two away is going to be, it's going to be illustrative of the spell checker, understanding spell checker, and it's good exercise for practicing filter.